Yeah, hi everyone. Thanks for coming to my talk today. Thanks Data Spartans for hosting this event. It's been really good. Thanks for inviting us. It's been a really good series of talks, and we really appreciate the chance to come up here and talk about the work we've been doing at Tytn on building quantum-inspired AI compression. Yep, so this is me. I'm Jamie. I'm the co-founder of Tytn. I co-founded it with two other PhD students from UCL, and now Miriam's come on board, who's in the audience today. I don't have a good LinkedIn picture of myself, so these are the only pictures I could find before this event, so that's me with all my menagerie of dogs. And today, what we're going to talk about is some of our work on building AI model compression platforms using these quantum-inspired techniques. So AI is facing a really big problem today, and when I say AI, there's a lot of different ways to define AI. I mostly mean deep learning, and in particular, really large deep learning models. The things that you see powering NLP and computer vision models today, rather than things like random forests or gradient boosted trees or whatever. And so these large deep learning networks have grown exponentially in the last few years, and hardware really can't keep up with this. And so if businesses want to deploy these large models to power the next generation of their applications, they're going to have to do something to close that gap. And we're hoping to be the people who do close that gap, at least in part, by leveraging some of the ideas we actually saw in the last talk to compress deep learning models. And so this problem we've called the deployment problem. I think other people know that's slightly different, but that's what we mean by the deployment problem, when models are so large that you can't run them efficiently as in the back end of commercial applications. So looking at graphs like this, it's really clear that the deployment problem is going to come to a head eventually. So these large NLP models, and I think that's what all these models are, they process natural language, have been growing exponentially in the last few years. And some of the largest ones, like the Switch C at the top right, are really mind-bogglingly large and really are nowhere near the point where they can be deployed on normal computers. More sort of schematically, the way we see this evolving as time goes on is as this growing deployment gap, where you'll see that the models that are deployed at the back end of applications that companies are making money from will stall as the hardware capacity stops growing. But the state-of-the-art models that people like Google and Facebook and NVIDIA are producing will keep growing, but they just won't be used in commercial applications. So the way we see this happening or playing out as things stand is that companies will have a couple of options. A, they can deploy the state-of-the-art models as produced by Google or NVIDIA or something, and pay that extremely high financial cost, and also, as we've seen as a recurring theme in these talks, the extremely high environmental cost of deploying these models. As a result of that, they get a better model, they get a more powerful application, but they also lose a few really valuable things, like having data privacy. You need to transfer the data back and forth, maybe internationally really high-powered data centers, and you lose the ability to run on the edge. And a lot of sort of IoT devices are expected to be where a lot of value is driven for AI models. And the other thing companies might do to avoid some of this is to deploy lower spec AI. So maybe they train something from scratch themselves using just their in-house data. And this will have a lower environmental cost and a lower financial cost, probably still both quite high. But you'll lose the power in that model, and sort of some unscrupulous competitor who doesn't care so much for the environmental cost might just outcompete you or just spend loads of VC cash to outcompete you. And it's likely that these models will still be difficult to deploy on edge devices because edge devices are just hard to deploy to. So we think that the way to bridge this gap, to offer a third option, is to train these really large foundation models and take the ones that Google and NVIDIA are making and find a way to compress them to try and match their performance whilst also keeping costs low. So what we hope to make is a platform that can give you all these things in some sense. You have a lower environmental impact by deploying much smaller models and reusing the training from the foundation models. You don't have to retrain models. Having a much cheaper cost to deployment, being able to run models locally or on edge devices to keep privacy high, and to have lower need for labeled data, which is often the most expensive part of machine learning projects, because you can reuse the pre-training of the big foundation models. So the process that we've come up with to do this really has three tenets to it. And when you put a large model through this process, hopefully at the other end you get a small model. And these three tenets are model tuning and runtime optimization, which are quite common in the machine learning field as targets of research, but also our own quantum-inspired model compression using the tensor network ideas that were introduced actually in the last talk. So I'll talk a bit about why we call this a quantum-inspired compression, not just because it's a cool name, but we actually use ideas from quantum mechanics. So as you heard in the last talk, that as system sizes grow, the computational complexity grows exponentially needed to represent them. So if you have even a relatively small molecule with 100 electrons or so, the size of the vector needed to describe it, if you wanted to do numerical calculations, would be 2 to the 100 complex numbers in order to exactly represent it. And this is probably on the order of every supercomputer combined together in the whole world, maybe times 100 or something. I don't know, it's a big number. But to get around that, for years, people who work in quantum physics have come up with a clever way of compressing a large quantum state, like you see on the left, by representing it as a graph or a network of smaller tensors that when you multiply them together, the result is a far smaller, when you multiply them together, the result resembles the original quantum state, but storing the tensors is much smaller and can be done on normal computers. Now, due to the similarity in the mathematics behind numerical quantum computation and deep learning, you can do this exact same process on deep learning models. You can take a neural network on the left, run it through this tensorization process, and out the other end, you get a much smaller deep learning network that in some way mimics the original large model. So in early experiments, when we've been working with these ideas, we've got some really promising results. We worked with satellite companies in the UK to train computer vision models to detect clouds that can run on the satellite, and you don't have to stream 4K images down to the Earth, which is seen as a real enabling technology for real-time inference on satellite images. And using this tensor network-inspired deep learning compression, we were able to compress state-of-the-art vision models down by 10 times to make them fit onto a satellite and run on board, whilst beating the current state-of-the-art, which was hand-tuned by the ESA, the European Space Agency, and it beat that by about 10% in accuracy as well. So this process of compressing pre-trained, powerful large models seems to do better than training similarly sized models from scratch, because you make use of the resources that I think Google had trained the original model that we then compressed. And we see that doing so for large language models can give a big cost saving, which I'll go through in a second. We estimate that, if you can get an effective 8 times compression of a large language model, you can get up to a 96% cost saving, which I'll break down in a minute. And we see a 5 times speed up in language model inference when this sort of technology is applied. So with compression, we see as there being 5 really large impacts. One is that you get a faster route to profitability. You can do more with less labeled data. You can deploy models to the edge. The AI becomes more sustainable. And models can be run on local hardware, running in a business rather than on the cloud. So let's look at how this sort of thing might increase a route to profitability. And the basic problem at the heart of this is how expensive cloud computing has become. So if you have a large language model, or any large model really, and due to either size constraints or latency constraints, you need a couple of NVIDIA A100 GPUs, which isn't unheard of, needing that sort of thing, then the monthly cost of that is around $4,000 a month if you don't pay for some sort of bulk discount. That was at least when we checked in June. But if you can get that running at the same speed or down to the same size that you can run it on a single T4, then the cost savings you get is about 96% from the original, which is about $50,000 per model. And it's likely in a lot of commercial applications that you'll run, even if you train a model once, you'll want several in deployment, either to help with flexible demand, or you want personalized models for individual users or things like that. So these costs really can rack up very quickly. these two benefits, running on the edge and running on local hardware, are a pair of benefits that I think are really valuable to certain industries. So in things like health and finance, data privacy is really important. I can imagine there's lots of hospitals and banks that don't want their data being sent all around the world to run on machine learning models and would like to run them in-house. And in healthcare, we see things like IoT models being really important, where people can track data on their watch or on their phone, and it gives them information about whether they should go see a doctor or on their blood levels or something like that. And other people that care a lot about running their models on the edge or locally are defense and space. I talked about space a second ago. One benefit that we think isn't talked about much in the compression space is that about needing less labeled data. So when you fine-tune a really large pre-trained model, typically you need a lot less data in order to achieve the same performance as if you trained it from scratch. And this is quite easy to see because, I mean, Google has their proprietary 300 million image data set or something. If they've trained a model based on that, then you get that benefit without needing to use. So that model already has a good understanding of things like shapes and colors and textures. You don't need your data set to teach it that. So by compressing these large pre-trained models, we think companies can get a lot more value with a lot less data. And data collection and labeling and cleaning is often quoted as one of the most difficult parts of machine learning projects. And finally, powerful AI obviously can become more sustainable. The T4 GPUs we mentioned earlier use a lot less energy than the A100s. And since models will stay in production much longer than they're trained, and maybe the total number of inferences will be far larger than during their training, by reducing the amount of energy used at deployment time, we think that'll go a long way to reducing the environmental impact of AI as a whole, even though we're not aiming to reduce the training time. So if you want to see any of these benefits in your own companies or your own projects, get in touch. Maybe we can make one of these work for you, and I'll be happy to take any questions.
Any questions?
What is the investment for scaling down a model in terms of what kind of time is usually required to achieve that compression?
Yeah, so I think typically the time taken to compress is on the order of the training time, as in, so it's like a fine-tuning process. So however long it would take something to fine-tune, it's approximately the same size. Because although you're training something smaller, you're not training it from scratch. So you get a lot of the benefits of having this model, in some sense, having seen lots of data already. So typically it's about the order of fine-tuning, which is less than training from scratch.
And a second question with that then, if you are in a case where you can apply transfer learning and you're just fine-tuning the top layers, then would you apply that before doing the compression, or could you do that to a compressed model?
You could also do that to a compressed model. I think the benefit that we see is being able to take advantage of models that really couldn't be produced commercially. And you can train something from scratch, but like the largest efficient net, the efficient net family was all trained on a closed source data set, which is extremely large, probably couldn't be used in a commercial setting. But because you have access to these models, in some implicit way, you have access to this data set. And any compression now takes advantage of this pre-training on a data set that you wouldn't have access to. So in some sense, we see the compression paradigm as being more powerful than the pre-training and fine-tuning on your own available data.
Thanks for the talk. What do you see as the relationship between the rate of compression and the rate of accuracy loss? Is it linear? Is it exponential?
Yeah, it's kind of hard to say. So accuracy loss, no one really knows how these deep learning models work. But in some sense, people think they try to memorize data sets. In some sense, they capture all the things from the training set and compare to this memorization. And so the things that you tend to lose first are the complicated stuff, the things that are confusing or real edge cases in your data set. That seems to be what you lose first when you do this compression. And so in some sense, you can overcome this. You can view this in a way as a bit like Hoffman coding, where if something's rare, you you give it a lot of computational power, and you link to some maybe larger model. And if something's very common, you link to a very small model, in the same way that if a number appears a lot and you want to compress it, you give it a small code word. If it appears very infrequently, you give it a large code word. So the small model will lose the complex edge cases, but the large model will keep them. So you can have like a pair of models, one which gets called very infrequently on the very obscure edge cases, and one that gets called very commonly on the very common cases. And that's typically what we see when we do this sort of compression.
And one more question. Is there a floor to the compression?
Probably. I mean, typically, like, you just want to pick something sensible. Like, you pick maybe the most powerful thing that meets all of your cost and latency constraints. But I imagine there is, right? Like, linear regression is optimal, right? Linear regression is optimal for, there's no better that you can do for a linear regression. You can't find it. There's not a better linear regression than the ones that the algorithms give us. So that might be a flaw, right? If I reduce the number of parameters, it's only going to go down from there. That's like probably the flaw that I would give. As like one parameter for each feature. However good that is, that's probably the flaw.
Thanks a lot for the talk. So I was wondering if calibration was an issue that is being triggered by this compression, because some of the models that have grown a lot lately suffer a lot from miscalibration, where they're not able to address when they're certain or uncertain. Is this something that you've came across with your compression techniques, or is this something that remains unchanged?
So what do you mean by calibration?
So models have grown a lot in terms of accuracy lately. Models from the 2000s were able to recognize when they were right and when they were not. So nowadays, the big ones are normally quite accurate, but they're usually unsure of when they're right and when they're not. Mm-hmm. And this is, I've been working with skin lesion datasets recently, and one of the issues we have nowadays is that even though we're quite accurate, our models are not able to recognize when they're actually right about their prediction or not.
Yeah. So I think that still remains as a problem, because the things that we compress to are still look a lot like standard deep learning models. So they suffer from a lot of the problems that deep learning models have, like explainability and I guess this lack of calibration. I imagine there's some proposals out there about how to model the uncertainty of these things. Like if your final layer is like a probability, then presumably this is like a proxy for uncertainty. Maybe not a very good proxy, but yeah, largely all the problems of deep learning remain when you compress, because you compress to other sort of deep learning models.
All right. Thank you very much.
Yeah, I have one question. So how much the technique generalizes? I mean, we have several network architectures. We have convolutional, we have transformers, you have graph neural nets, which are kind of transformers. So how does it look inside? Give us a little bit of a glimpse. Is it the same tensorization that works for all the nets, or do you have like verticals and different architectures that are different versions of the same basic technique? How does it look inside?
Mm-hmm. Yeah, so what it looks like inside is that it makes matrix multiplication a bit faster and a bit smaller by doing it approximately. So that's one way you could put it. And so anything that has large vectors multiplying large matrices can be compressed and potentially accelerated by these techniques. And so that is very general. That's a very general paradigm. And that includes most deep learning architectures. I think graph neural networks are an interesting one because I don't know whether there's a way you can factorize these adjacency matrices. So you might have to store those in memory, and then you don't really get much of a speed up. But I'm sure some of the graph experts could tell me that there is a way to do that, and then you could get this sort of acceleration. But yeah, it's a very general technique. And for pure compression, it works pretty ubiquitously. If you also want to speed up on that, you have to work a bit harder because it doesn't necessarily have like optimal memory layouts. Like GPUs are quite well optimized for large matrix multiplications. But for compression alone, it's very general.
Any more questions from the audience? Good. So, Thank you, Jamie.
Thank you.